This is Physics 104A, Chapter 14, homework. The topic is wave motion. We start with number 25. A simple harmonic wave, wavelength 16 centimeters, amplitude 2.5 centimeters, propagating in the negative x direction. We need to find angular frequency, wave number, and an expression describing the displacement of the wave. I write out the information given: wavelength, amplitude, speed, and the angular frequency omega is 2 pi times f, which is 2 pi times speed times wavelength, so we get 13.7 radians per second. And I'll use two significant figures and say 14 radians per second. Question B, the wave number, that's k, it's 2 pi over lambda, so we have 0.39 per centimeter. For question C, the wave displacement formula, y as a function of x and t, is in the format a cosine kx plus omega t, and so we'll just plug in the numbers, being mindful of the units, so I've written out the full units within those numbers. 2.5 centimeters times cosine of 0.39 per centimeter x plus 14 per centimeter t. Number 28, a transverse wave, the amplitude's given, there's the frequency, string is under 21 newtons tension, mass per unit length 15 grams per meter, determine its speed. The equation is V equals square root of force divided by mass per unit length. Just make sure you have it in MKS units, so 21 newtons divided by 15 times 10 to the negative 3 kilograms per meter. Square root it and you get 37 meters per second. Number 29 uses similar concepts. There's the amplitude, the wavelength, the speed, and mass per unit length. Find the tension, and so it's going to be the same as if it were a string. It's the spring tension. So force is v squared times mu. Notice that much of the information that's given here is irrelevant. All we need is v squared 6.7 meters per second squared times 0.17 kilograms per meter. We get 7.6 newtons. Number 49. Transverse waves propagate 18 meters per second when there's 14 newtons of tension. What will be the wave speed if the tension is increased to 40 newtons? Okay, similar concept to the last two problems. Here I've written out the given information. We have V1 and F1. V2 is unknown and F2 is given. If we take the equation of V equals square root of F over mu, going back to number 28, what I'm going to do, actually even better, let's go to number 29 where the square root is gone, F equals V squared mu. What I'm going to do is put everything that is changing on the left and everything that's constant to the right. So that gives us F over V squared equals mu. And the reason I'm doing this is so that if mu is unchanging, and by mu I mean whatever's left on the right hand side, I can just say it's constant. So if F over V squared is constant, I don't really care what mu is. The point is F over V squared is constant. So we can set it up and say F1 over V1 squared equals F2 over V2 squared. We know all those values except V2, so we're going to solve this for V2. V2 is the square root of F2 over F1 times V1. So we have square root of 40 newtons divided by 14 newtons times 18 meters per second, and we get 30 meters per second. Number 59. Number 59, at a point 15 meters from a source of spherical sound waves, intensity is 750 milliwatts per meter squared. How far do you need to walk so that the intensity is 270? I've set it up with the given information. We know R1 and I1. We don't know R2 and we know I2. And the way I'm going to solve this problem algebraically is similar to the previous problem, to the way I did number 49. I'll take intensity is power over 4 pi r squared. I'll take this equation and put everything that's changing to the left, everything that's constant on the right. So we have intensity times r squared equals p over 4 pi, which is constant. Since I squared is constant, we can say I2 R2 squared equals I1 R1 squared. And we can just ignore p and 4 pi. We'll then solve for R2. So R2 is the square root of I1 over I2 times R1. Plug in the numbers that we know and we get R2 is 25 meters. Then we look back at the question and see what is it asking. The question is not asking simply the new distance, but how far do we need to walk? So we need to walk 10 meters away, 10 meters farther away. For number 64, the intensities in watts per meter squared of sound with intensity levels of 65 decibels and -5 decibels. We'll use this equation. Beta is 10 times the logarithm of intensity divided by the intensity for threshold of hearing, 10 to the -12, and those units would be in watts per meter squared. And solving for it, we're solving this algebraically for I. I've first divided both sides by 10, so we have beta divided by 10. I've split up that logarithm. Instead of the logarithm of a ratio, I've got the difference of two logarithms. So logarithm of the numerator minus logarithm of the denominator. I've got minus log of 10 to the -12, and that would be minus -12, which is plus 12. Now I'm solving for log of I. So log of intensity is beta divided by 10 minus 12. And when we turn this into an exponential equation, it becomes, since it's logarithm base 10, we've got 10 to the beta 10 minus 12 equals I. And that's converting the equation in this line from a logarithmic equation to an exponential equation. Once we have that solved for I, we'll just plug in the decibels, and the first one is 65, and so that gives us 10 to the 6.5 minus 12, it's 10 to the -5.5, and we get 3.2 times 10 to the -6 watts per meter squared. Question B is -5 decibels, so that's -0.5 minus 12, that's 10 to the -12.5, which is 3.2 times 10 to the -13 watts per meter squared. Finally, number 67. Excuse me. Alright, try that. Number 67. At 2 meters from a sound source, you measure the intensity level as 75 decibels. How far away must you be for the perceived loudness to drop in half? Which means to an intensity level of 65 decibels. All right, we have R1 and beta 1 are known. R2 is unknown. We're given beta 2. And so what we can do, we're looking for R2. And so we can say the change in beta, which is beta 2 minus beta 1, is 10 times the logarithm of I2 divided by I1. We know that beta 2 minus beta 1, that's going to be 65 minus 75, so that's -10. When we divide both sides of the equation by 10, just to get rid of that 10 that's on the right-hand side, we have -1 equals log I2 over I1. Okay, now we have to deal with the distances. And so we have this I2 over I1. What we want is something, an expression that deals with those distances. And so we've got I2 over I1 is power, P is power, over 4 pi r2 squared. I1 is power over 4 pi r1 squared. Many things divide out, and we're left with r1 over r2 squared. So we can replace in the logarithm equation, instead of I2 over I1, we can replace that with r1 over r2 squared. So back to the logarithm equation that we left off up here. Now we have -1 equals logarithm of r1 over r2 squared. Using some rules of logarithms, let's take that little 2 up there and move it to the, make it the coefficient on logarithm. So it's -1 equals 2 times log r1 over r2. Divide both sides by 2. Now we've got a logarithmic equation that we can set up as an exponential equation. Since the logarithm is base 10, we can say 10 to the -1/2 power is r1 over r2. So there we have 10 to the -1/2 power r1 over r2, which means that r2 is r1 over 10 to the -1/2 power. We plug in, we know that r1 is 2 meters, so 2 meters divided by 10 to the -1/2 is 6.3 meters. And that's the end of the Chapter 14 homework set.